Alright, we're going to start with this simple example. We just have a 2 kilogram block sliding at 10 meters per second horizontal surface where we do have friction. 0.2 is the coefficient of kinetic friction. How far will it slide? So I've already drawn a free body diagram here. We've got the gravity force 20 newtons. Normal force will also be 20. It's on a horizontal surface, so they will balance out. Friction force, I've gone ahead and solved that here, 4 newtons. Okay, so how I'm going to solve how far it's going to slide, I'm going to use the work-energy theorem. So that states that the net work equals the change in kinetic energy. So the net work, force times distance, and then we'll have 1/2 mv final squared minus 1/2 mv initial squared. The force we're talking about is the net force, that's the friction force. Now I'm going to call that negative 4 newtons because it's opposing motion, and I know friction in this case is doing negative work because it's opposing the motion. The distance, that's what we're looking for, so we'll call that d. Okay, how far will it slide? That implies that it's going to come to a rest, so the final kinetic energy will be 0 minus 1/2 mass is 2, initial velocity 10 squared, so we get the block will travel 25 meters. Okay, now part 2 of this problem, I just want to look at the energy here. So I'm going to look at the initial energy of the system. Okay, so initially it's moving, so it has kinetic energy, and that's 1/2 mv squared. So 1/2 mass is 2, speed is 10. So the initial energy then is 100 joules. How about the final energy? Okay, well, final energy, it comes to a stop, so it has no kinetic energy. It's not up a height, so it has no gravitational potential energy, so our final energy is 0. So here we have an initial energy of 100, final energy of 0. We've talked in class that we've got the work done by friction that's going to go into some thermal energy. So it doesn't actually disappear, it just transforms into thermal energy. Alright, so now let's take a look at how much work friction does. The work done by the friction force. Okay, well, work done by the friction force is going to equal the friction force times the distance it's traveling. So work done by friction, friction force is negative 4 newtons, and then the distance it travels, 25 meters. So the work done by the friction force is negative 100 joules. Okay, so if our initial energy is 100 joules, our final energy is 0, the work done by friction negative 100, things are starting to make sense. And in class, we looked at the equation initial energy plus the non-conserved work equals the final energy. Alright, so when we look at these numbers, our initial energy is 100 plus non-conserved work, negative 100, equals our final energy, which is 0. It always adds up. So this non-conserved work is important because that's taking energy out of our system. In this case, it's the work done by friction. In most cases in our class, that's what it's going to be. Now that non-conserved work, an important point here is it's always negative. Okay, you should end up with a final energy that is less than your initial energy. It's taking work out of the system. Okay, all right, that sets up the non-conserved work. Now let's look at the next example and apply this to a more complex problem.